This is FRM Part 1, Book 2, Quantitative Analysis, and the chapter on multivariate random variables. Now, hopefully you just read the chapter on random variables, where we suggested that a random variable might be a function of some other random variable. Let's take a simple example here. Let's suppose we're trying to evaluate and examine bond prices, and we know that bond prices are a function of the yield to maturity on that bond. And so we could establish that relationship between those two variables. And we talked about probability mass functions and probability density functions, and we compared discrete random variables with continuous random variables. We're going to do this again in this chapter, but what we're going to do is we're going to add some extra random variables. I remember when I was in graduate school, our professors would say things like, you know, when that yield to maturity on the bond goes up, the bond price is going to fall, and that yield to maturity is able to capture lots and lots of different information like credit risk and maybe interest rate risk and maybe liquidity risk and maybe other kinds of risk. And I remember sitting there thinking that that's a lot of pressure to put on the yield to maturity of a bond to be able to look out and scan the entire environment and reach out and capture all of those important facts and can summarize itself right in that one yield to maturity figure. And that's what we're doing in this chapter. We're saying, okay, bond prices, they might be a function of yield to maturity, but they also might be a function of something else. You know, a quick example, the bond price for a company like Coca-Cola, which, you know, gets the vast majority of its operating cash flows outside of the United States. You know, the bond price might be a function of its yield to maturity, but it also might be a function of, you know, U.S. exports and imports that are functions of things like trade and tariffs and taxes and government regulations and consumer taste throughout the world, et cetera, et cetera. So that's why this chapter is called Multivariate Random Variables. So lots of stuff that you learned in the previous chapter is going to apply to here, but we're going to add another dimension to it, as you'll see in some of the diagrams that I have. So let's get to the learning objectives. And these things look an awful lot like they did in the previous chapter. We'll start with a probability matrix. We'll talk about expectations of functions, and then we'll go ahead and take a look at how random variables relate to each other. We'll discuss covariance. We'll discuss correlation, we'll discuss transformation, then we'll kind of add those into, you know, what traditional investment analysts call portfolio analysis. We'll look at the variance and then conditional expectations. And then we'll end with a slide on identically and independently distributed random variables. And so that should take us through this chapter. Let's go ahead and start with just a simple definition of these multivariate random variables. What they do is they accommodate the dependence between two or among more random variables, like that example I was giving you earlier about the yield to maturity and the trade balance. The multivariate analysis is informed by the fact here, and this goes back to my example, in most scenarios, we're really trying to figure out how these random variables can simultaneously impact some variable that we're trying to study. And there's a couple of examples in the circle points. Boy, don't you guys really get frustrated when you go to the doctors and the doctor says, hey, let's run 57 different tests. And then you have to wait for those results. But maybe one test result is going to be indicative of something else and something else and something else. And then, of course, what's more relevant for us as risk managers is states of the economy or the rating by the credit ratings agencies or maybe the returns on credit default swaps as they determine rates of return on things like stocks and bonds. Now, I said this in the introduction, when we're considering discrete random variables, boy, what was that example that we talked about in the last chapter? Like maybe rolling the dice, right? You have just 6 possible outcomes. How about the winner of the Kentucky Derby race every year, first Saturday of May? There are always 20 horses in that race, right? Only horse 1, 2, 3, right out to 20 can win. So that's when we consider the probability mass function. But when the random variable is continuous, then we need to go into something else, and we call that the probability density function and the cumulative function as well. So there I have in Roman numerals 1 and 2 the properties of the PMF. All the probabilities must be greater than or equal to 0. You can't have a negative probability. That makes sense. And the sum of those probabilities must be 1. Of course, if you have 2 states of the economy and you have a 10% chance of one state occurring, then the other state has to have a 90% chance. And then, of course, you remember the pictures that we drew of the normal distribution, but we also drew exponential and maybe a uniform distribution and some other kinds of distributions. And so what we're trying to do is we're trying to determine what the probability of a component that is less than or equal to some given value. You know, for example, getting back to my Coca-Cola bond example, we could say something like, hey, you know what? The realized rate of return on a Coca-Cola specific bond last year was 6.5%. What's the probability that we're going to get more than 8% during the course of this particular year, or less than 4%, or you can do all that kind of stuff. And so what you're doing here is you're either looking at that normal distribution, right, that bell-shaped curve, either the cumulative probability leading up to that point, which would be the less than, or the cumulative probability after that point, which would be greater than. So you can use that table and that graph and that picture to answer both of those questions. All right, let's look at a bivariate. So there's 2 of them, discrete random variable distributions. So look where those 2 x1 and x2 bars kind of meet down there at the origin. And so I want you to pretend that you're a little stick man or a little stick woman, and you're right where the x1 is, and you're looking that way. All right, you're looking 2-dimensional. And so what you can see is that at the origin you start out with just a little block, but then as we move to the left, then we increase, right? And then if you're the stick man or woman over with the x2, you're looking at it this way, and you can see, kind of the same relationship. But suppose that we have some kind of variable that we're trying to examine that depends on both x1 and x2. So you have to take a step back and look at this from 3 dimensions. So we're going this way, and we're going this way, and plus we're going up as well. Now, there's only so much you can get from looking at this, at this picture. And for someone like me who's very, very sensitive to motion sickness, I look at this and I get motion sick. I feel like I'm on an airplane. So what makes life easier is to put this in tabular form. So let's take a look at an example here. Look at the first block point under the example. We're examining financial markets. Market sentiments play a role in determining the return earned by a security. All right, so suppose that the return earned by a bond is in part determined by the rating given to the bond by the analysts. All right, so let's simplify life here. There are only 3 possible bond returns: minus 10%, a 0%, or a plus 10%. The analysts who follow this particular security can only give 3 ratings. They can be positive, they can be neutral, or they can be negative. And so let's summarize this in a probability matrix. And so inside, so notice we have down the left-hand column, we have the analyst, which is our second random variable. So that's either +1, 0, or -1. And then the bond return, that's our first random variable. That can be -10, 0, or 10%. And then embedded in that matrix are the associated probabilities given those 2 random variables. All right, so what can we do? What can we do with this probability matrix? Well, what we can do is look at each of those cells inside of this matrix and define them as the probability of a joint outcome. So look at the orange I have there. So the probability that we lose 10% by investing in this bond, coupled with a positive outlook by the analyst, is just 5%. And you can do that for each of those other 8 probabilities inside of that matrix. Now, the next slide is going to show us, all right, surely you're looking at this matrix and thinking, all right, you told us that those probabilities, they have to be 0 or positive. So that shows up here. And then you said something like, oh, well, the probabilities need to sum to 1. And I don't know if those probabilities all sum to 1 in there, but they probably do. So that's what we're going to do. We're going to sum the columns, and then we're going to sum the rows. And of course, we're going to call those marginal distributions. All right, so let's take a look at that first column with a minus 10% bond return. So we got the 5 and 10 and 20. So we sum that to get to 35%. So we have a 35% chance of getting a minus 10%. And then let's just read along the bottom, a 20% chance of getting 0% and a 45% chance of getting 10%. So, boy, can I do that math quickly? 35 and 20 is 55, and then 45 is 100%. So there's where those probabilities then sum to 1. The next question is, how can we continue to apply these things? So just like we summed going down the columns, let's go ahead and sum over to the rows, and that gives us 40 and 35 and 25%. And so 40 and 35, what does that give us? 75, and the 25 gets us up to 100. So that represents those marginal distributions. So look at my circle question there. Are they really independent? It's clear that these two variables are not independent, because when you multiply their marginal PMFs, that does not get us back to that joint PMF. And look what I have in the parentheses there, that 5% does not equal the 35 times the 40%. Now, how about let's move on to conditional distributions. So let me just swing back here. Let's suppose that, in this probability matrix, we're summarizing the probabilities that relate to x1 and x2 variables, right? But now let's ask the question. Let's suppose that we know one of those two variables. Like, for example, we know that the analyst has assigned our bond a negative return. Then what happens? And so we're going to call that the conditional distribution. And there's the definition of the conditional distribution. That should be relatively familiar to you there in blue in the middle of the page. And so notice what I've done with that picture in the back. At the bottom, this is that first picture. And let's go through this quickly so I don't get vertigo here in just a second. But notice that in that back row, let's call it, those are bolded. So we're going to say, hey, let's suppose that we know that's where we're located on this graph. And then what happens? So let's go ahead and look at an example here. What we can do is we can very easily compute the expected bond return. I've done that at the bottom. All we're doing is taking 35% times the minus 10, 20 times the 0, and 45% times the plus 10%. We did that way back at the beginning of all of these chapters. So our expected bond return turns out to be 1%. Now let's go ahead and conditionally expect what happens. All right, so look at the example. What is the expected bond return conditional on a positive analyst rating? All right, so this is what I'm suggesting back here. We know we're in that blocked point, that bolded point there in the back, and then what is going to be our return? So here's a good starting point. We know that given this entire probability matrix that our expected bond return is just 1%, right? And let's forget about the mathematics that it turns out to be 1%. But surely we can say to ourselves, all right, we're not interested in this bond at all. But given these numbers, let's go ahead and now say, what happens if the analyst gives our bond a positive rating? Well, clearly, let me just go back here quickly. Clearly, when we compute this expected bond return given a positive rating, we're eliminating the negativity and the neutrality, right? So it's got to be bigger than 1%. And so here it turns out to be 6.25%. And so notice how we're going to compute this. We're going to do it the exact same way, but notice the expectations there. I have x1 slash x2 conditional on the analyst rating. And so what we're going to do is use those marginal probabilities over on the right-hand column as the total, right? So we're going to say minus 10% times 5 over the 40, and then 0% times 5 over the 40. There's another 5 in there. And then 10% times 30 over the 40. And that gets us really, what's the best thing that can happen given that the analyst is going to provide a positive rating? Well, that's going to be that 6.25% conditional expectation. All right, what we're interested now is measuring the relationship between two random variables. Now, you might remember that I gave you guys this example in a video a while ago in which I let you in my classroom. And what I do, I teach in a finance lab, and there's a little alleyway right in the middle, and I have students sitting here and students sitting here in rows, and they're looking in. So I can walk up and down. So when I'm teaching them about covariance and correlation, I always do the following. I say, all right, here's one random variable. And I say, here's Jim standing and I'm walking. And so I might take a couple of steps, and I'll say, okay, here's one random variable. It's the number of steps that Jim takes, but maybe it's the rate of inflation over the next couple of years. And then I'll go right next door to myself, just maybe half a step over, and I'll take different steps. I'll stutter step, and then I'll take a big step, and I'll say, let's suppose this is the return on the Japanese yen. How do we relate those two? Well, the fact that I was walking in the same direction means that there's a positive relation, right? When inflation goes up, then the return on the Japanese yen goes up. Now the question is what is that magnitude of that relationship? And that's what covariance does. So it gives us positive, negative, or zero relationship down at the bottom there, but it also tells us the strength of the relationship. Now, those of you who are mathematically inclined, which is virtually all of you guys, there's an equation for covariance. And really what we're trying to do is say, well, when one variable is this far away from its mean, let's multiply it by the other variable, which is this far away from its mean, given some, certain discrete interval there. And so you just multiply all those and you sum all those and you get the covariance. Now, here's the thing about covariance is that covariance can be almost any number. Look at the bottom there. It could be positive, but it could be 412. It could be 0.639. It could be negative. It could be a minus 0.000721, or it could be a minus 3 million. Now, it could be 0. So if it's 0, then it's just 0. And so because we're taking the product of the difference between, an outcome and the mean here and the outcome and a mean over here, it can be almost any number. And the covariance is very difficult to interpret. It's a product, right? You don't go to the food store and say, oh, I'm going to buy 12 potatoes and I'm going to buy 6 pieces of fish. You don't go and say, oh, I'm going to buy 72 of potatoes and fish. That doesn't really make any sense. So what we need to do as good statisticians is we need to standardize the covariance. And that, of course, is what the correlation coefficient is. So look at the equation for correlation. It's the covariance in the numerator, which could be any number, right? Positive or negative or 0. We're going to divide it by the product of the two standard deviations. And so this is what I always do to my students. I say, look, covariance can be any number within this range. But in order for us to make some kind of a reasonable and coherent conclusion about the relationship between two random variables, we need to put that covariance in a vise. So get your work table out and put the covariance in a vise and start turning it and squeezing it till it gets down to something that's manageable. What's over here? Minus 1.0. What's over here? Plus 1.0. Now we have some economic meaning tied to covariance. So remember, correlation and covariance, they pretty much measure the same thing, but correlation is a standardized covariance. So what do I have in the interpretation there? I bet you guys know this from a previous lecture. So strong positive linear relationship when correlations are positive, and then negative, of course, and then 0. So what does that mean? We go up to 1. A 1.0 positive correlation means there's a perfectly linear relationship. So in class, this is what I do. I take 2 or 3 steps here, and then I come over here and I take the same 2 or 3 steps, and I say, what's the relationship between Jim's number of steps? And the students say, hey Jim, they're identical. And I say, yes, that's positive 1.0 correlation. And then I do the same thing. I take 3 steps this way, and then I take 3 steps backwards. And they say, hey, Jim, you went backwards. That's just the opposite. So that's a -1 correlation. And then for 0 correlation, I might take a couple steps here, and then on the other side, I'll go up a half a step, and then back 1.5 steps, and then up 2 steps, and then there's no relationship. So thank you for bearing with me on that very simple explanation, but I have found that has worked really, really well, both with undergraduate and MBA students. All right, last chapter, there was a couple of good slides and some really good stuff inside of the chapter about linearly transforming these random variables. And remember, we talked a little bit about the motivation for doing this. I mean, sometimes you do it just out of convenience. Sometimes you have this idea of testing a linear relationship. You really don't know if it's linear, so you transform them, and then you see if the relationship is in fact linear. And then sometimes you might want to get rid of the third moment of the distribution, which is skewness, or the fourth moment of the distribution, which is kurtosis. So there's lots and lots of reasons to linear transform these random variables, and we can use the equation for a straight line. So that's what we're doing there. Notice I have a plus bx1 and then c plus dx2. Now the cool thing about this relationship is that when 2 variables are linearly transformed, then the covariance really is not going to have much of a change. In fact, there'll be no effect. I mean, it might shift it up or down a little bit, but the covariance is going to stay the same. So look at the bottom block point. Linear transformation does not change the correlation. All right, that should make perfect sense. Now, how about the variance of 2 random variables? And you guys should look at that first blue equation and think, yes, I learned all about that in my investments days. So the variance of x1 and x2 is going to be the variance of x1. So you have the variability in the first random variable. We're going to add the variability in the second random variable, and then we have to add the covariance between those 2. And you put a 2 there because x covaries with x1 covaries with x2, and x2 covaries with x1, so you get twice the covariance. Now here's a good simplification. If the covariance between x1 and x2 happens to turn out to be 0, then those random variables are independent, and then that third term just gets wiped out. Now, let's suppose that we're putting these random variables inside of a security portfolio, like a stock portfolio or a credit default swap portfolio or some other portfolio. And so we have to weight x1 and x2. And that variance of x1 and x2 combined by the parameters a and b, notice that a plus b has to be equal to 1, then we've got the same formula that we have up above, but we have to weight it by the square of a and the square of b, and then we've got to throw a and b inside of that third term. So that bottom equation down there is really just the formula for the variance of a 2-stock portfolio. All right, how about if we switch solely to continuous random variables? And so notice that first block point. That's a really good one. It's a really useful one. Same concepts, same methodologies as the discrete random variables. And so let's get back to my motion sickness here. Let's pretend we're the stick man or the stick woman looking at x1, or over here on x2. And now we're looking at this 3-dimensionally, but instead of having the blocks, go up this way and the blocks go up that way, now we have a smooth line. You remember in the last video for random variables, I told you to think about this as a wave. You're standing there in the ocean and the water's up to your waist and the wave is coming at you. And so that wave kind of could look a little bit like a normal distribution. And so what you're trying to do is slice portions of that wave. And of course here when we have two random variables, x1 and x2, you're just slicing it two ways. You're slicing it as it comes at you like that. You're thinking, okay, boy, if it was just the first part of the wave, that wouldn't affect me. But you have to go all the way up to the top of the wave and maybe it'll tumble you over. And then you look at it this way, you're trying to slice it in just the opposite direction. Now, of course, we need to use our calculus here to determine things like first moment of the distribution and second moment of the distribution as well. But this picture is really cool because if you look at it as the stick man or stick woman from x2, notice the shadow looks like a normal distribution on that back wall. And that's what you're looking at as, if you're looking at it from just the perspective of the second random variable, it looks like just a regular two-dimensional bell-shaped curve, as it does from the stick man or stick woman position there at x1. There could be another bell-shaped curve along that other back wall. But we know this. We're stepping back here, and so we're looking at it three-dimensionally. And then, of course, this conditional PDF or continuous random variable. And by the way, there's that equation in black right there at the top right. And so this is what I was talking about, about slicing it. So if we're looking at it from the perspective of x2, we're taking a look at that wave and we're trying to slice it and get rid of the first part of the wave so that we can just look at the back part of the wave. And remember, we can slice that wherever we want. We can slice it at the beginning, we can slice it at the top, or we can slice it at the end. And so note the example that I have there over on the left, in the middle of the left, the x2 variable could be just interest rates, right? And so what are these interest rates doing? These interest rates are flowing at us like a wave. They're, interest rates change every second of every day, so they're flowing at us. And then what we want to know is what's the loss associated with that new or that marginal or that next interest rate. And that's going to be that first random variable. So we take the slice out of it and we say, oh my gosh, look, if interest rates go way, way up, we're going to have, oh, wait a minute, interest rates go up, bond prices go way down. Boy, that could be a huge loss. As opposed to if we're slicing, the first part of the wave, if interest rates go up by a little bit, then we're not going to have that big of a loss. Do you see where this all ties in? What we're trying to do is we're trying to use these continuous random variables and their PDFs to try to help us come up with some estimate of value at risk or better our understanding of the probabilities associated behind the expected losses, or what happens, those small probability events that have huge consequences. How about identically and independently distributed random variables? This is important here. So identically distributed random variables really means that there are no overall trends, which means the distribution really does not fluctuate. Independent means that those items are not correlated, going back to our covariance and our correlation coefficient. And so the classic example is this, the coin. You flip it and it's heads, and then, well, you might say, oh, I'll flip it again and it'll be heads because it was heads before, but that doesn't work. I learned this lesson one of the first times I went to Atlantic City, and I was watching the roulette table. It's the black and it's the red. And this was years and years ago. In Atlantic City, they had a listing of whether it was red, black, red, black, red, black. And I remember looking at these things. And even if it was red, let's say 5 or 6 times in a row, there was no way that it was going to be red with more than a 50% chance. Of course, it's less than 50% chance in Atlantic City because, right, they have the 2 green things. So anyway, this is a good example. How How about the mean and variance of these identically and independently distributed random variables? All right, so look at this. i.i.d. variables have the same moments, right? Mean, first moment, variance, second moment. Therefore, it is easy to manipulate them. Now, when we say manipulate, we don't really say manipulate so that we can figure out what we want and then produce those results. But what we can do is we can manipulate them so that they can be in the form that we want so that we can make some reasonable conclusions. All right, so there's the normal distribution. There's the mean of mu and the variance of sigma squared. The expected value is going to be n times that common mean. So notice over there, we're summing from I equals 1 all the way up to n. So we just multiply n times u, and then the expected value of x of this random variable is going to be mu, and then the variance is going to be n times that variance. And that takes us through these learning objectives. Hopefully what you learned here is the 2-chapter sequence. So we started in that previous chapter, random variables, and then that was one random variable, right? And then we added a couple of other ones here.